Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arifbhat.me. The other way is to download the uh, notebook files from course GitHub account Arif PUCIT, and all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture 6.4 of the sixth module, overview of machine learning, for the course titled Tools and Techniques for Data Science. Well, we all know that at an abstract level, machine learning is the application of AI that gives the machine the ability to learn without being explicitly programmed by understanding the relationships between the input features and maybe the output label of the given dataset, and then formulating that relationship in a mathematical form. My dear students, in the previous two sessions, we have practically understood the simple and multiple linear regression and the math that do all the magic behind the curtain. Today we are going to do a scuba diving to have a crystal clear understanding of the math involved in gradient descent and how to use it to solve linear regression problems. So with this premise, let us move on to the learning agenda of today's session. Well, my dear students, today's session is mainly about gradient descent algorithm, which is the most important and most fundamental algorithm in all of deep learning, and is also used in machine learning and artificial intelligence. In fact, I will not be wrong if I say that without gradient descent, deep learning would not have existed. In order to set the stage right, we will spend some time to revise some basic calculus concepts which are a must to know before digging out details of gradient descent algorithm. Then we will understand the algorithm theoretically before we apply it to find the local minimum of a differentiable function using Python code. And we will explore the challenges of gradient descent algorithm, like the local minima and unfortunate starting point, vanishing gradient problem, and exploding gradient problem. Finally, we will take a toy dataset and will perform linear regression on it using gradient descent algorithm. My dear students, if you want to jump on a specific subtopic, you can do so by clicking the link in the timeline below in the description box. So let me start with section 1, and that is overview of some related concepts of calculus. Well, we do talked about derivatives in our previous sessions, previous two video sessions, and which is of course a key concept if you want to understand how systems change in time. We all have studied derivatives in our first year calculus course at university as well. When I was preparing this current video, I received an email of one of my students in which she requested to give a bit of more time on revising the concepts of derivatives. And since derivatives play an important role in understanding the gradient descent algorithm, so I thought it appropriate to spend around 25 to 30 minutes to derivatives. If you already have a fair idea about derivatives, you can skip this section and can jump on to the next session by just clicking the timeline below. Okay, so before we start, let me first define calculus, which is a branch of mathematics that deals with calculating the derivatives and integrals of functions and their properties. The two main branches of calculus are differential and integral calculus. Well, this differential calculus deals with rate of change of something with respect to another thing and slopes of the curves. And this integral calculus deals with accumulation of quantities and areas under or between the curves. And this is shown in this image at at an abstract level. My dear friends, before we discuss as to how we can calculate derivatives of functions, let me start by giving you an intuition behind derivatives. Consider this graphical representation of a hypothetical function shown by this curvy red line plotted between two quantities, distance and time. Well, the distance is the dependent variable plotted along the y-axis, while time is the independent variable plotted along the x-axis. And let's suppose that this graph represents the movement of my car while I was driving from my home to my office. And these 1, 2, 3, 4, 5, these 5 different points on this red curve, of course, have different slopes, showing the rate of change of distance with respect to time. Well, at this fourth point over here, you can observe that distance is not changing, roughly from time unit 5 to time unit 8, which shows that the car is stationary. Okay. Let me describe this using the graphical representation of two specific functions. F of x is equal to 3x plus 2 and f of x is equal to x squared plus 2x plus 2. This linear function f of x is equal to 3x plus 2 is graphically represented by a straight line in this left graph. And this nonlinear function f of x is equal to x squared plus 2x plus 2 is graphically represented by this parabola. Well, this left graph, this shows the equation of a straight line of the form y is equal to mx plus c with a positive slope of 3. A positive slope of 3 means for every 1 unit increase in x, f of x increase by 3 units. Moreover, since this is a straight line, so the slope is the same or constant throughout this line, whether you calculate it at this black point or you calculate it at this red point. Now consider the graphical representation of f of x is equal to x squared plus 2x plus 2. Shown in this right graph, which is a parabola. And since it is a curvy line, so the slope is not constant. Rather, slope is different at different points of this curve. The slope at this red and black points are actually nothing but the slopes of the tangents drawn at these 2 points. At this red point, the slope of the tangent is negative 8, which means for every 1 unit increase in x, y or f of x decrease by 8 units. And similarly, at this black point, the slope of the tangent is positive 12, which means for 1 unit increase in x, y or f of x increase by 12 units. 1 unit. My dear friends, let me conclude by saying that the slope of a non-linear function will be a function itself, which can be achieved by differentiating the original function. And to calculate the slope of a specific point, for example, let's say x is equal to 5, you substitute 5 in the derivative of that function, which becomes 2x plus 2, so we get a slope of 12. Don't worry if you haven't understood it. This is what we are going to learn in this section. Okay, in order to find the slope of a function at a specific point, we need to differentiate that function. In our undergrad course of calculus, we have learned 2 techniques of differentiation. One is using differentiation rules and the other is by first principle. Let me first give a quick recap of using differentiation rules to differentiate a function. First of all, the constant term rule. Well, this constant term rule says that since a A constant has no variation, so its derivative or slope is always 0. This elementary power rule says that you multiply the function by the power and subtract 1 from it. This is shown in the formula over here. Well, this constant multiples rule says that uh, you bring the constant out and then take the derivative of the remaining part of the function. And finally, this sum rule states that you take the derivatives separately and then sum them up. Let us apply these rules on some polynomial functions for better understanding. And for that, to verify the result, I will be using the symbolic math or SymPy library, which offers a rich set of APIs for performing computer algebra. If you haven't installed SymPy, you can do that by executing this code, as it doesn't come bundled with Python, so you have to install it. Okay, let us differentiate this polynomial by applying the above discussed rules. Please do it using paper and pencil before you execute the code of this cell for auto differentiation. Instead of using the Python print function, I'm using the IPython display method of its display module, which is a general purpose tool for displaying different representation of objects. Well, this symbols method of SymPy, this transforms strings into instances of symbol class. Since we have just one symbol, so I have kept it over here. And over here in this line, we are using the symbol x to create a function 5x cubed plus 3x squared minus 7x plus 20. Finally, the diff method of SymPy is pass the function and the symbol with respect to which you want to differentiate the function. So this is the function and this is a symbol with which I want to differentiate, and I get the differentiated function in this df, and then I use the display method of IPython display module to display it. Let me execute the code. Great. So this is the differentiated function. So this 3 comes out, 5 to the 15, 15x squared, 1 is reduced from the power, 15x squared, the first term, 6x, this is 6x, and this is minus 7. I hope this makes sense. Okay, now consider this function x cubed plus 1 and find out the slope or derivative of this function at point 25, which is nothing but the slope of the tangent drawn at this point. Let me execute this code. So the differentiation of the function is 3x squared, and in order to calculate the slope at point x is equal to 2, simply put x is equal to 2 over here, and you get 12. This is what it is. Let me execute the code for this third example as well. And you see the slope or derivative of this function at point x is equal to 9 is 0.66. I hope this makes sense. Okay, my dear students, the next rule, the one that is used in gradient descent algorithm as well, is the chain rule, which helps you find the derivative of nested functions. Actually, you just split the complex function into simpler functions and then you multiply the differentiated outer function with the differentiated inner function. This is shown in this formula over here. Let's do an example to understand it. Consider this function 2x squared plus 8 whole square. Let this inner function 2x squared plus 8 be u. So y is equal to u square. First compute dy over du shown over here, which is of course 2u, and by substituting the value of u we get 4x squared plus 16. Now compute du by dx, which is simply the derivative of the inner term, that is just this 2x squared plus 8, which comes out to be simple 4x. And finally, we just have to multiply the differentiated outer function with the differentiated inner function, and this comes out to be this. Let's verify this using SymPy. Let me execute the code of this cell. Great. My dear friends, do practice differentiating these examples. Let me execute this code, and let me execute this code as well. Please do it using paper pencil for better understanding. And let me move ahead to the next rule, and that is the product rule. Well, the product rule of differentiation is different from the sum rule. Let me describe it with the help of this example function, x times the square root of 2x plus 1. Well, there are two terms. You multiply the first term as such with the derivative or differentiated second term, plus you multiply the second term as such with the differentiated first term. So in this case, our answer is 1 over 2x plus 1 square root. Let me execute this code to verify what SymPy says. Great, the same answer. Okay, finally, this quotient rule. This rule is used when there is a division of two functions. The numerator of the quotient rule formula is quite similar to the product rule, but having a minus sign. The other difference is the bottom term, this z, comes first. Moreover, in the denominator we have the bottom term squared. Please use paper pencil to do this example at your own time, and I have worked it out for you. Let me verify it using SymPy. Well, the answer given by SymPy looks a little different, but it is same. Our answer is a little bit more simplified. Moreover, the slope of this function at point 4, 6 can be obtained by substituting 4 in this derivative, which comes out to be minus 1.5 or minus 3 by 2. Great job done. My dear students, I have discussed differentiating polynomial functions only. You can practice differentiating trigonometric, exponential and logarithmic functions at your own, as I don't want to make this section a complete course on calculus. Let me move ahead. Let me move ahead and talk about differentiating functions using first principle, which is a technique that uses limits to compute the slope of a tangent line at any given point along the curve. Imagine that we have a generic function whose graphical representation is shown in these three graphs. Consider this leftmost graph and suppose that we want to find the slope of this function at point x0, which is the slope of the tangent line at this black dot on this blue curve. Now we know that to calculate the slope of a line we need at least 2 points. Consider this middle graph now, where I have taken 2 points on the curve. The first point is x0, f of x0, and the second point is x0 plus delta, f of x0 plus delta. Well, this green dot corresponds to x is equal to x0, while this yellow dot corresponds to x is equal to x0 plus delta, where delta is a small value, a small change in x. Now if I connect the green and the yellow dot with the line, it will be a secant line, and of course we can calculate the slope of this line using the formula that is y2 minus y1 over x2 minus x1. But this is not the line which we need. We actually need the slope of the tangent line at this green point. So to make this secant line more close to our required tangent line, we need to take this delta and make it smaller and smaller and smaller unless it reaches almost 0. and this is what is shown over here in this right graph. Well, the complete process is shown over here in this animation that I have taken from Wikipedia. So the differentiation using first principle can be written as this red function. So the limit delta approaches to 0, where delta is a very small value, very small change in x. My dear friends, let me describe this using a concrete example now. Consider this function x squared plus 2x plus 2. This top left graph shows the graphical representation of this function. And suppose I want to calculate the slope of this function at x is equal to 2, somewhere over here. And if we substitute 2 in this function, we get f of x or y is equal to 10. So this is shown in this middle graph, 2 comma 10, x is equal to 2 and y is equal to 10. So this is the point. In this top right graph, I have taken delta as plus 3. This is 210, the delta is plus 3, so the new yellow point is 5, and if we substitute 5 in this function, we get 37. So these are the 2 points. Now in this bottom left graph, I have calculated the slope and the y-intercept of this secant line, which comes out to be 9 and minus 8 respectively. So this 9 is the slope and this minus 8 is the y-intercept. I hope this is making sense to you. Now in this bottom middle graph, I have reduced the delta to 2.1. Over here the delta was 3 and over here the delta has been reduced to 0.1. So the function so the points are 2 comma 10 and 2.1 comma 10.6. Well, in this right bottom graph now, I have once again calculated the slope and y-intercept of the line between these 2 points, which is almost the tangent line, having a slope of 6.09. So the derivative of this function, as we can calculate using the power and sum rule, is 2x plus 2, and if we substitute x is equal to 2, we get the slope, which is 6, which is quite close to 6.09. Great job done. My dear friends, if you haven't understood this, please rewind this part, listen to it again, and proceed only if you have a clear understanding of differentiating using first principle. Well, after understanding it visually, let's do it analytically using a paper pencil. The differentiation formula is shown over here in equation 1. To calculate the derivative at x is equal to 2, we substitute x naught is equal to 2 in equation 1 and we get this equation 2. Now we substitute f of 2 is equal to this and f of 2 plus delta is equal to this in this equation 2, and we simplify it and we arrive at this value shown in equation 3. Now you can apply the limit and you get the slope at x is equal to 2 of this function, which comes out to be 6. Okay, finally let me do the same task using the Python code. Okay, over here. So I have defined the function named f, which is x squared plus 2x plus 2. Then I have defined another function that is a derivative of that function, and this deriv function is passed a function and the value of x and the small value of delta, and it returns the slope using the formula, of course, y2 minus y1 divided by x2 minus x1. This third argument, remember this Third argument is a very small value. Okay, let me execute this code. And now over here in this code cell, I'm just calling the deriv, that is the derivative function, and passing it the three arguments where f is the function, 2 is the value of x, and this delta is actually over here a list of different delta values. So let's execute this code. You see, for a very small value of delta, the slope almost becomes 6. And finally, we can calculate the value of y-intercept using the line equation, that is y is equal to mx plus c, which comes out to be -2. I hope this is making sense. So we have understood the concept over here. We have done it using paper pencil. Then we have done it using a Python code. And finally, let me graphically draw the function x square plus 2x plus 2 and the tangent line at point 210 using matplotlib. Well, my dear students, this subplots method of pyplot module of matplotlib library creates a figure object and axis objects. Over here, I'm just creating a single axis object. Well, these three lines of code are creating a line plot of the function x square plus 2x plus 2 for the values for the x values -10 to +10. Well, this single line of code is drawing a dot at the point 2 and 10. These 5 lines of code are drawing the tangent line for the slope 6. I think the slope is 6. Yes, we have calculated it above. And the y-intercept of -2. This m is 6 and this c is basically -2. And remember, these are the slope and the y-intercept values which we have calculated above. Let me just execute it. Great. So this is the function, this is the point, and this is the line or the derivative of this function at this point. I hope this is making sense. Okay. My dear students, please do these two tasks at your own time. Use the first principle to calculate the derivative or slope of these two functions using paper pencil, and then verify your answer using Python code. Later to visualize, draw the graphs of these functions as well as the tangent lines at these specific points. And I am moving ahead. Okay, now we have a fair idea about computing the derivative of a function at a specific point. Let me touch upon another important related concept, and that is maxima and minima of a function, which are the largest and the smallest values of a function respectively within a given range or maybe on the entire domain. And collectively they are known as extrema. Okay, consider this blue curve that shows the visual representation of a hypothetical function. Now the question is, how can we identify the extrema points in this function? Well, in case of a one-dimensional function like this, we can visually see those points easily. However, in case of a multi-dimensional function, it becomes quite difficult to visualize. Well, anyway, the derivatives and gradient comes for our rescue. Well, 1, 2, 3, and 4. These 4 extreme points A, B, C, and D are the corresponding values of x where the function has a derivative of 0. Now the $100 question is, which out of these 4 points are maxima and which are minima? Well, you can find the answer to this question by looking at this blue line closely. The points x is equal to A and x is equal to C are the local minima, because these are the points where we have a negative derivative towards the left and a positive derivative or slope towards the right. Similarly, these 2 points x is equal to b and x is equal to d. These are the local maxima because they have a positive derivative to their left and negative derivative to their right. Okay, fine. Now consider this fourth order polynomial of single variable f of x is equal to minus x4 plus 3x square, shown in blue. Well, this left graph shows a blue curvy line that is visually representing this function. And there are these three extremas represented by three dots. Well, the derivative of this function is mathematically given in this green expression, that is minus 4x cubed plus 6x. In this right graph, this derivative function is represented by this green line, along which I am moving my mouse. Further note that all the three extreme points are associated with a derivative of 0. Observe that this green curve crosses through the 0 line at 3 points. 2 out of these are maxima and 1 out of this is the minimum. Over here you can see that after calculating the derivative of the function, I have equated it to 0 and solved for x. And since the derivative function is a third order polynomial, so we are getting three solutions, and they are x is equal to 0 and x is equal to plus minus square root of 3 by 2. In this right graph, these 3 points are represented by these two red dots and this white dot. Now this white dot is the local minimum because the derivative is negative on its left and positive on its right. Similarly, these red dots are the maxima because they have positive derivative to their left and negative derivative to their right. I hope this is crystal clear now. Anyway, to ensure that you have understood the concept of minima maxima, here is a nice animated GIF that I have taken from Wikipedia, which shows all the concepts that we have discussed so far. So this is our trigonometric function, and this blue line shows its graphical representation. You can see a point moving along the curve, and at each location the derivative or slope is being displayed at the bottom. If it is positive, it is shown in green, and if it is negative, it is shown in red. Soon you will see, once this point will come up over here where we have a negative slope, this will be red. Great. Fine. And there are 5 locations or points where the derivative or the slope of this moving tangent line becomes 0. These are the two minimas, because here the derivative or slope is negative to the left and positive to the right. And the remaining two are the maximas, because over here the derivative or slope is positive on the left and negative on the right. Moreover, this point over here is the problem point. You will see that over here where my mouse is hovering, the derivative is 0. But it is neither a maxima nor a minima. This actually turns out to be a problem for gradient descent algorithm, which is called vanishing gradient. And of course, I will later see why this happens and how to solve this problem. Let me move ahead. My dear students, for completeness, let me talk about partial derivatives as well. We have seen functions with a single variable. We have plotted them in a two-dimensional graph and have calculated their derivatives, which gives us the slope of those functions at a given point. Let us repeat this for functions having two or more variables, in which case we need to take the partial derivatives. Well, consider this example 1, where we have a function of two variables, x squared minus 3xy. So first we compute the partial derivative of this function with respect to x and treat the other variable y as constant. The first term becomes 2x and the second term becomes 3y. So the partial derivative of this function with respect to x is 2x minus 3y. Similarly, while computing the partial derivative of this function with respect to y, the first term x squared is treated as constant, so its derivative is 0, and the partial derivative of this entire function with respect to y becomes minus 3x. Please do refresh your memory by calculating the partial derivatives of these remaining examples as well. And do note that in example 3 and 4, over here we have functions of three variables, therefore we have three partial derivatives. So in case of two or more dimensional functions, there is a derivative along each dimension. In example 1, the partial derivative with respect to x means that we ignore y and we just see how is the function changing over x. Similarly, the partial derivative with respect to y means that we ignore x and we just see how is the function changing over y. And finally, the list of these partial derivatives is called gradient. So the gradient of a function at any point is just a collection of all its partial derivatives with respect to all the dimensions of that function. My dear friends, partial derivatives are usually indicated by this funny looking curvy symbol. More importantly, the gradient is indicated by this upside down triangle called nebula. And it is just a collection of all the partial derivatives with respect to all the different directions or dimensions of the data, and this is shown in green over here. Excuse me. Okay. My dear friends, consider this function x squared minus 3xy, and let me take 10 random values, 10 x's and 10 y's, which I will like to pass to this function x squared minus 3xy func to calculate the value of the function at these two values. Let me execute this. So these are the two x and y arrays, and this is the value of that function. So for x is equal to 2 and y is equal to 2, we have f of xy is equal to minus 8 and so on. I hope this makes sense. Well, in order to plot a 3D axis object, I'm using the axis method of the PyPlot module and passing it projection argument as 3D. The default is 1D, which is actually the type of the coordinate system. Well, after that, these three lines, I'm using the labeling the x, y, and the z axis. And finally, over here, I'm using the scattered 3D function and passing it the three arrays. Over here, this percentage matplotlib notebook is a cell magic and is useful if you want to interact with your 3D graphs. Let me execute it for understanding. So great. So this is the graph. Using the cell magic, we have this graph with which I can interact with. I can move and rotate it. This is the x, this is y, and this is f of xy. You can play around and rotate this 3D scatter plot as it suits you. Moreover, if you move your mouse inside this graph, the corresponding x, y, and f of xy values are displayed in the right bottom of this figure. You can see that. Well, the way we have created a 3D scatter plot, we can also visualize the same function, that is x squared minus 3xy, as a surface. For the x and y values over here, in these two lines, I've used NumPy linspace method to create 20 points in the range of -5 to +5. And to create a grid of XY values, I have used the mesh grid method of NumPy. And finally, over here I have used the plot surface method to create a surface plot. Let me execute the code of these cells. Great. So you see, we have a mesh grid. We have a surface plot, x-axis, y-axis, f of xy, and once I move my mouse inside, I get the different values on the x, y, and the z-axis. You can rotate it as per your requirement, whatever suits you. I think this is okay. Anyway, fine. My dear friends, let me finally calculate the gradient of this function x square minus 3xy at point x is equal to 4, y is equal to 2. One way is to calculate the partial derivatives using differentiation rules and substituting values of x and y. So the gradient comes out to be, if I substitute the values over here, the gradient comes out to be 2 and 12, minus 12 rather. Moreover, as we have done before, we can calculate the gradient using the first principle. Here I have made minor changes in the derivative function. Over here, you see, it is passed three arguments. First is the function name. This second argument is the index of the argument list with respect to which we want to differentiate. And the third argument, that is asterisk args. This means that it takes variable number of argument list, which are the values of the variables where we want to calculate the derivative. Well, this first line is the delta value, a very small value. I have taken 0.00001. In this second line, we are calling the function fn and passing it the value of x and y to compute the output. And the actual magic is being done in these three lines. We are increasing only that variable whose index is passed via this idx. And then we are actually calling the function fn and passing it the incremented value of one variable and the other variable and the other value as such without any change to compute the output. So we have the two output values. One is f of xy and the other is f of xy1. So we can easily calculate the slope by using the formula y2 minus y1 over delta or x2 minus x1. I hope the code makes sense. Let me execute code of this cell, defining these two functions. And now over here I am calling this derivative function, passing it the name of the function fn. Well, this second argument 0 means do partial differentiation with respect to x and calculate the derivative for x is equal to 4 and y is equal to 2. Let me execute it. So this is the same answer. And let me calculate the partial derivative with respect to y. So this is minus 12. Great. Good job done. My dear students, we are done with section 1. I'm sure that after understanding the concepts discussed in this section about derivatives, gradients, and finding the minima maxima of a function, the understanding of the gradient descent algorithm will be a piece of cake for you now. And let me start by saying that the gradient descent algorithm is the most important and most fundamental algorithm in all of deep learning and is also used in machine learning and artificial intelligence. In fact, I will not be wrong if I say that Without gradient descent, deep learning would not have existed. Okay, instead of straight away jumping on to the algorithm and its Python code, let me describe gradient descent using a very famous analogy that you will find in old literature shown in this image. Suppose you decided to go on a hiking trip up a mountain one day. It has gone dark and you want to go down to flat land. Unfortunately, it is so dark that you can't see which side is up and which side is down. So you decided to feel the slope of the ground under your feet. And this is shown in figure 2 in the top right image. And obviously, remember, this is an analogy for the derivative, since the slope is essentially the derivative or the gradient in case of multiple dimensions. My dear students, after determining the slope of the ground under your feet, the first natural question is in which direction to take the next step. The answer is whatever will reduce the slope or the direction that feels the most downhill. In simple words, if the slope is negative, as shown over here in figure 2, you move right. On the contrary, if the slope is positive, you move left. The second question is the size of the step to take. And the answer is it should be proportional to the slope value. In case of steep slope, you take bigger steps and vice versa. And this is shown over here in figure 4. You see initially the slope is steep, so we are taking bigger steps. And at the end the slope is not steep, let's suppose, so we have taken smaller steps. The third natural question is when to stop. When to stop this iterative process? The answer is when the slope becomes 0 or when the next step doesn't reduce the slope anymore. It is natural that when the slope under your feet is equal to 0, it means that you have reached the flat land. Now we have an intuition about the gradient descent algorithm. Let us now understand it in a formal way. My dear students, gradient descent is actually a first order iterative optimization algorithm for finding a local minimum of a differentiable function. The idea is to take repeated steps in the opposite direction of the gradient of the function at that current point. Let me describe this definition with the help of a pseudocode and a graphical representation of a function x squared plus 2x plus 2. And consider this left graph and the corresponding pseudocode. Our objective is to find the local minimum, which is shown by this green dot at x is equal to almost minus 1. We start with a random guess. Let's suppose x is equal to minus 9. Then we calculate the slope of this function at this point. The derivative of this function is 2x plus 2, and by substituting x is equal to minus 9 in it, we get a slope of minus 16. And since the slope is negative, so we move right, that is, we move in this direction. We move right by just increasing our previous guess, that is, the previous guess was minus 9, so we increase it, let's suppose by plus 3, and our next guess of the minima is now minus 6. I compute the derivative now at x is equal to minus 6, which comes out to be minus 10. Once again, since the slope is negative, so I move right by increasing my previous guess by plus 2. And my next guess of minima is now x is equal to minus 4. I iteratively repeat this process until I reach to the value of x where the slope or derivative of this function becomes 0, and that is x is equal to minus 1. Now consider this right graph, excuse me, and the corresponding pseudocode, of course. Over here I have started with the random guess of x is equal to, I think it is 8, it is not, yes, this is x is equal to 8, and the derivative of the function at x is equal to 8 is positive 18. Since the slope is positive, so we move left by decreasing our previous guess. We decrease it from 8 to 5, then 5 to 2, and so on. We continue until we reach the value of x where the slope becomes 0, and that is once again x is equal to minus 1, the same answer. Okay, now let me describe the pseudocode of the gradient descent algorithm. Okay, the first line over here, guess is equal to minus 9, is the random guess of the local minimum from where we want to start. The second line is the number of iterations, normally called epochs. Here I have kept it very small just for understanding. Its value should be kept reasonably large, otherwise you might not be able to reach your destination. Okay. Then we enter this loop, and inside the loop, this is the line where the actual magic is happening. This line, guess is equal to guess minus step. Well, if the slope or gradient is negative, as shown in this this left graph, the step becomes negative, and when we multiply it with the negative sign, it overall becomes positive and is added to the guess, and we move towards right. My dear students, this is important to understand. Let me repeat it again. The magic is in this line. We need to update our guess using a step value. The step value is equal to the learning rate times the slope. If the slope is negative, which is the case over here, this overall value becomes positive, so it is added to the guess and we move right. On the contrary, if you see in the pseudocode over here in the right, over here the slope is positive 18, so this step value is subtracted from the guess and we move left. I hope this makes sense. Well, anyway, the another important parameter over here in this algorithm is the learning rate, which is a very small fixed number. Normally, we take it as 0.01. This is kept small so that you should not take very large steps and miss the target. And remember, this step is actually a multiple of learning rate and the slope or derivative or the gradient. And if the slope is large, the steps will be large, and if the slope is small, the steps will be small. That's why over here you are seeing larger steps, and when the slope gets smaller, you see smaller steps. Okay, so good job. Let me move ahead. My dear students, now we have a fair idea about the gradient descent algorithm at an abstract level. Let us make our hands dirty by practically implementing it in Python. Once again, consider this function 3x square minus 3x plus 4, whose derivative is 6x minus 3. And when we equate its derivative to 0 and solve for x, we get 1 over 2, which is the value of the minimum of this function. Let me import NumPy and Matplotlib. So this is the function fx, which is passed x, and it returns the value of the function at that value. Similarly, this deriv, this derivative function, is passed x and it returns the value of derivative of the function at that value. Let me execute the code. I'm hard coding it and not using the first principle. Now, code of this cell is actually the plotting function, and its derivative using the plot method of the pyplot module. I am using the values of x from -2 to +2, 2000 random values. Let me execute the code of this cell. Great. Well, my dear friends, this blue line, this blue curve, a sort of parabola, represent the function 3x square minus 3x plus 4. And this orange straight line represents the derivative. Excuse me, which is 6x minus 3, which is the equation of a straight line with y-intercept of minus 3, as you can see over here where my mouse is hovering, and the slope of course is positive 6. Further note that the minimum of the function is the value of x where this derivative has a value of 0, which is I think this point, and where we have x is equal to 0.5. As already said, this is easy to visualize for a one-dimensional function, but is really difficult when we move to multiple dimensions. Let's move ahead and find the local minima of this function using a gradient descent now. Well, this code cell actually implement the gradient descent algorithm as we have discussed it in detail already. Note the three parameters: our initial guess, learning rate, and training epochs. See the magic line inside the loop, which is actually updating the minimum guess with a step that is a multiple of learning rate and derivative of the function at current minimum guess. Hope this makes sense. Let me execute it. Great. Note that we started with the initial value of -2 and a learning rate of 0.01, and with 100 training epochs we reached a result of 0.49. Let me change the initial guess to +2 now and run the algorithm again. Note that this time the answer is 0.503. My dear students, you see that the gradient descent algorithm is not giving us the exact correct answer, which is 0.5. Before it was giving something 0.49 and now it is giving 0.503. But it is giving us pretty close results. Let us now plot this local minimum point on the graph, and this code cell do this job. Let me straight away execute it. It's simple. Note the red dot on the derivative line is roughly at 0.5, and this is the place where derivative is 0. Good job done. Now before moving any further, let me move up to gradient descent algorithm again over here and explore the effects of these two parameters, the learning rate and the training epochs on the gradient descent algo. Well, this learning rate is the value that scales the minima or gradient as we update our minimum. Let's change the learning rate to let's suppose 1 and execute. Oops. You see a huge number, a totally incorrect answer. Now let me change it to a very small number. Let's suppose 0.0000001. Okay. And let me execute it again. We started from 2 and we ended up at 1.99. Not at all anything close to 0.5. So it did get closer but didn't reach the destination after 100 training epochs. Let's execute the next code to visualize it on graph. So you see this is the place where we have our dots. So we started from location 2 and we have just moved a little bit. Let me make it to a reasonably small number and do it again. It is again at the same place. Let me reduce it to this and do it again. So you see it has moved a little bit, but it has not reached the destination. Okay, so let me now increase the value of the training epochs to, let's suppose, this value. I think now this will be correct. My dear friends, before you move ahead, please make it your habit to play around with these hyperparameters, and these are the learning rate and the training epochs, which have a direct impact on your results. And of course, the initial starting guess also have impact on what the final result you will get. Let me say that when you have a very small learning rate, you need to have more iterations because the model is going to learn more slowly. So play around, spend some time, change the parameters, try to gain some intuition as to what happens when you change the three parameters. That is the initial guess, learning rate, and the training epochs. Let me move ahead. And let me move ahead and talk about the challenges of gradient descent algorithm. My dear friends, remember gradient descent algorithm is not guaranteed to give us a correct solution. And there are several circumstances that can make gradient descent algorithm go completely wrong or maybe just a bit wrong. And the first is poor choice of model parameters as already discussed. The second is the algorithm is stuck in a local minima. The third is vanishing gradient problem. And the fourth is exploding gradient problem. Let me quickly describe these. Okay, consider this trigonometric function cos of 2 pi plus cos of 2 pi x plus x square. And this is graphically represented by this blue line, blue curvy line in this graph. If you have taken the calculus course, you should know that the derivative of this function is minus 2 pi sine of 2 pi x plus 2x, which is graphically represented by this orange curvy line in this graph. Okay. Well, please ignore this typo in the legend of this graph. The derivative should have been written minus 2 pi sine, not minus 2 sine. Anyway, well, you can visually see there are four local minima shown with these dots. Do note that the slope of the blue line is negative on the left and positive on the right of all these points. If in gradient descent algorithm you make your initial guess of suppose minus 2 or say minus 1.2 over here, the gradient descent algorithm will give you the local minimum of x is equal to minus 1.4, which is not correct. Similarly, if you make your initial guess of say plus 2 over here, then gradient descent will give you the local minimum of x is equal to 1.42, which is again incorrect. You will get to the green or purple minima only if your guess falls between these location minus 1 to, let's suppose, plus 1. So my dear students, in case of complicated functions, it really becomes difficult to arrive at a global minimum. One possible solution to this is that you use a stochastic gradient descent instead of batch gradient descent. And of course, I will talk about stochastic once we are done with batch. Anyway, let me move ahead. Well, vanishing gradient is a problem that occurs when the gradient at slope becomes exponentially small. And then multiplied with learning rate, the step size becomes so much small that you don't reach the function minimum in a specified epochs. And this is shown in this one-dimensional function having only one minimum point. If you start from this location, you start moving right. However, do note this saddle over here where the function appears to be constant or almost constant, and the derivative over here is very close to 0. And we know that the step size is equal to the product of derivative and learning rate, which will almost becomes equal to 0. And therefore the training iterations or epochs will expire, and the gradient descent algorithm will not arrive at the optimal solution, which is somewhere over here. Well, in deep learning, there are different techniques that help in overcoming the vanishing gradient problem, like using activation functions that do not saturate, like this ReLU, that is rectified linear unit. You use long short-term memory or maybe gated recurrent unit. Our discussion on these is, of course, beyond the scope of today's session. Well, the third problem is exploding gradient problem, which is almost the opposite of vanishing gradient. Well, exploding gradient is a problem that occurs when the gradient or slope is too steep, and when multiplied with learning rate, the step size is large enough that we may miss the minimum. This is shown in this one-dimensional function graphically. So over here the slope is too steep, so our next jump will take us over here and we may not come up over here. Once again, there are different techniques to overcome this problem, like LSTM, gradient clipping, layer-wise adaptive rate scaling. Okay. Once again, our discussion on these concepts is beyond the scope of today's session. Hopefully, we will talk about these in our deep learning module, inshallah. Great. Well, my dear students, finally we are done with understanding the gradient descent algorithm. And I think we are now very well equipped to use it to solve the linear regression problem. But before I do that, let me give you a quick recap of our previous two sessions on simple and multiple linear regression, which we did using the ordinary least squares method. In those two sessions, our objective was to minimize the cost or error function called sum of squared errors, shown in green over here, where this yi is the actual value and this yi hat is the corresponding predicted value, which in case of linear regression is c plus mx or beta naught plus beta 1x, beta naught plus beta 1x. And of course we take the square of their difference to make the error function differentiable. Moreover, this value m represent the number of features and this value n represent the number of observations or data points. Well, having the data set, we have all these x's and y's, and the objective was to find these beta values that will make the value of this error function as close to 0 as possible. Well, for simple linear regression having single feature variable, we just took the derivative of this cost function and set it equal to 0, and finally we arrived at these two formulas of beta 1 and beta 0 shown in magenta color over here. Similarly, for multiple linear regression having two or more feature variables, we use the matrix formulation. We use the matrix algebra to calculate the derivative of the same cost function, and finally we arrived at this matrix formulation to compute the betas, all the betas as a vector, and this closed form solution is shown in red over here. My dear students, now $100 question is, when we can solve simple as well as the multiple linear regression problem using ordinary least squares method, why on God's earth we need to use the gradient descent algorithm to do the same? Well, the answer to this question is, when dealing with textual data or maybe audio or image data, the number of features in our dataset goes to millions, and the size of this matrix x becomes million by million. And since we have to compute the inverse of this matrix, and the time complexity of doing so with the Gauss-Jordan elimination comes out to be big of n cube, and of course that is too costly. So my dear students, gradient descent algorithm comes for our rescue, where we step by step move towards the answer using approximation technique. I hope this makes sense. Okay, I think now it is time to practically use gradient descent algorithm for a simple linear regression problem. Consider this toy dataset. Let me load this data from this CSV file. We have seen it before as well. It has just two columns containing the hours a student has studied daily and his or her acquired GPA in a subject. In our previous video session, we used the closed form solution to calculate the values of beta naught and beta 1 and have drawn the best fit line. This left scatter plot shows the 7 points, and this right graph also shows the best fit regression line that we used for prediction. The values of beta naught or y-intercept for this best fit line as calculated in the previous session was 0.89, and the value of beta 1 or slope was 0.46. Well, this right graph also shows the error function, which is the sum of squared errors. Now we will find these regression coefficients using gradient descent algorithm. Okay, excuse me. My dear students, consider this three-dimensional graphical representation of the error function for simple linear regression having single input feature. In literature, you may see this error function value being divided by 2n as I have shown over here. Well, the n in the denominator makes the sum of the squared errors to mean squared error. And this 2 in the denominator just make the calculation easy, as this 2 will come out after we take the derivative and will cancel out with this 2 in the denominator. Anyway, here is the beta naught, that is the y-intercept, and here is the beta 1, that is the slope, and over here we have the error function along the vertical axis, error function of two values beta naught and beta 1. We know in gradient descent we start with some random values of beta naught and beta 1, and then we keep updating them iteratively until we reach to the minimum value of this error function. The values of beta naught and beta 1, for which we have the least value of this error function, are then used for the best fit line fit. Also note that only two unknowns in this error function are beta naught and beta 1, as x's and y's as well as n are already known to us from the dataset. My dear students, since this is a function with two variables, so we need to find the partial derivatives. Okay, so let us first see how we can calculate the partial derivative of this function with respect to beta naught, which will tell us with a little change in beta naught how much error function will change. This is shown on the left of the graph. I think this derivation is a piece of cake, and finally we arrive at this simplified equation. Similarly, on the right side of this graph, I have shown the partial derivative of error function with respect to beta 1, that is the slope, which tells us with a little change in beta 1 how much error function will change. And finally, after simplifying, we arrived at this simplified equation. My dear students, if you closely observe the partial derivative equation with respect to beta naught shown on left at the end, and the partial derivative with respect to beta 1 shown at the end on the right, uh, you see that in case of a partial derivative with respect to beta naught, we have multiplied all the residual errors with 1, which is implicit over here. And in case of partial derivative with respect to beta 1, we have multiplied all the residual errors with xi, which is actually the input feature column related to beta 1. Well, in magenta color over here, I have written a generic expression for partial derivative of error function with respect to regression coefficients, beta m. And you see, we are multiplying all the residual errors with xi's of the mth column or feature related to beta m. I hope this makes sense. Okay. So for better understanding, I have taken our toy data set with just 7 observations shown over here. The values of x and y, study hours and the corresponding GPA. Let us substitute these values in this derivative expression over here. So once we put in all those values, we arrive at this equation 1. And similarly, by substituting the values of x's and y's in this derivative of error function with respect to beta 1, this is a typo. Let me correct it right over here. This is a typo that should not have happened, where I have to make the change. Okay, so this is with respect to beta 1. Beta 1 over here. Okay, sorry. So if we substitute these values in this expression, we arrive at this equation 2. So we have two equations. One is showing the derivative of the function with respect to beta naught, and the other is showing the derivative of the error function with respect to beta 1. Okay, and here we have the two functions, derivative of beta 0 and derivative of beta 1, which are passed the values of beta 0 and beta 1, and they substitute those values in these two equations to return the slope at that point. I hope this makes sense. My dear students, I have kept these things quite simple, and I have hard coded everything. You can write down generic functions as we have done above. Now we are ready and equipped to run the gradient descent algorithm to compute the two regression coefficients. Well, in step 1 over here, instead of guessing a single value, I am guessing two values. One guess is for beta 0 and the other guess is for beta 1. I have used 3 for beta 0 and 5 for beta 1. You can try other values as well. Well, in step 2 over here, uh, we are setting appropriate values for the learning rate and training epochs. I have chosen a learning rate of zero point 0.1 and have decided to run it in 500 iterations. And I think I have discussed in detail about the impact of these hyperparameters on gradient descent algorithm. Do make changes and run this code. Anyway, well, in this step 3, we enter into the training iterations where uh, these two magic lines are updating our random guess of beta naught and beta 1 with a step value. And the step value over here, of course, is the product of the learning rate and the derivative or slope of respective error function. And then, of course, I am just printing the updated values of beta naught and beta 1 in each iteration inside the loop. And after coming out of the loop, I am storing those values in beta 0 and beta 1. Let me execute it. Oops. So we have not executed this code. This code. Okay. Let me execute it again. Great. I just printed all the values so that you should have a fair idea. Our initial guess for beta 0 was 3 and beta 1 was 5. And you see we are moving closer to the results after each iteration. And after roughly, I think, 200 iterations, we are quite close to the result. Beta 0 is 0.88 and beta 1 is 0.46. Okay. I hope this makes sense. Fine. So finally, the values are for beta 0 we have 0.89 and for beta 1 we have 0.46. Great job done. Now we need to fit the line and do the prediction, which is again a simple piece of cake job. Well, this is the code which actually reads the study hours from this data frame and place it in a numpy array X, the GPA in a numpy array Y. Create the subplots, use the scatter plot method to plot the points, and I'm using the plot method over here. And for the plot method, I am using the X points of line and Y points of line. The X points of lines have been created using the linspace numpy method, 1000 points between 0 and 8. And using these points, I have calculated the Y points of the line using the line equation. That is y is equal to c plus mx. This beta 1 is the slope and this x is the x values. Let me execute it. Great job done. Okay, so now we have the regression line. We have the regression coefficients of the best fit line. We can use the line equation to predict the student GPA for any new input of study hours. Let's check out for GPA that corresponds to, let's suppose, 4.6. So that is 3.037. Great job done. My dear students, please make time and check out for the accuracy of your model. And let me close today's session by this task to do, which is really important to check your understanding of the concept discussed in today's session. Uh, Here is the same old dataset, advertising dataset. You need to use the gradient descent to calculate the four regression coefficients, as there are three input features: TV, radio, and newspaper. Interested students should try out the stochastic as well as the mini batch gradient descent as well, other than the vanilla flavor of gradient descent algorithm, that is the batch gradient descent which we discussed today. uh, and hope it will be fun for you all. I wish you all the best for this task till we meet in our next session of using Python's scikit-learn library for solving linear regression problems. And my dear friends, if you have liked this video, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.